The most important thing is that he is an associate editor of IEEE Sensor Journal, and of course, a distinguished lecturer of IEEE Sensor Council. Without taking any more time, I'd like to invite Jürgen to give the talk on wearable magnetic sensor and skins. Jürgen, thank you.
Yeah, thank you very much, Subhash. Thank you everyone else for joining this talk today. It's a pleasure to present this presentation about wearable magnetic sensors and skins to you. And I will actually dive right into the outlook of this presentation. I'm gonna give a short introduction about magnetic sensors, and then I will talk in more detail about mainly three magnetic sensors: Hall effect, giant magnetoresistance, and tunneling magnetoresistance, and tunnel magnetoresistance sensors, and also giant magnetoimpedance sensors. And these sensors I chose because they are thin film solid state sensors which can be used for wearable devices. And I will also give an overview about magnetic skins. All right, so magnetic sensors, first of all, they convert magnetic signals into electric signals. And typically what you are interested in is not really the magnetic field, but you're interested in something that is sensed through the magnetic field. So what you are going to measure is usually done indirectly. For example, the presence of an object where the door is open or closed, the angular rotation of an engine, or something like that. So you utilize the magnetic field and hence the magnetic sensor to actually detect a different physical parameter. And thereby one of the major advantages of magnetic sensing is that it is contact-free. The technology is actually quite old, and the first time that it appeared in history was 400 BC as the so-called south pointer, which was a device like this. It was a lodestone spoon on top of a plate, and the spoon would move as you rotated the plate, and it was not used for navigational purposes or something like that, but it was used by fortune tellers as a spiritual tool, and it's something that guided people in the way they figured out their environment or their lives. It was quite a long time later, 1044 AD, that the first mentioning of a compass was found in a Chinese war book. And it was the south pointing fish, which was made of a very thin iron leaf, and it was floating on water in a bowl, and it would point to the south and of course to the north. And this was the first time that the compass was mentioned, and it was about 300 years before it appeared in Europe, where it of course was exploited much more and quickly then made the appearance around the world. The traditional applications of magnetic sensors are manifold. Of course, we use them for rotational speed and angle sensors. We use them for position sensors as compasses. Then, of course, magnetic reading heads, also magnetic resonance imaging, which gives us the ability to visualize soft tissue as compared to X-ray, where we see the hard tissue. But there are many upcoming applications for magnetic sensors, like, for instance, in renewable energy, where they are used for current sensing in photovoltaic cells, or in early cancer detection, structural monitoring, miniaturized diagnostic tools in microfluidic systems, and rather recently also in magnetic random access memories. We have evolved quite a lot, and our sensors nowadays, they can be nanometrics in size, and we can detect even single magnetic beads of a micrometer or so in size, which is typically used in biomedical applications. Here, for instance, you see a Hall cross, which is a common setup for a Hall effect sensor in a microfluidic channel with the current loop being used to attract magnetic beads. And the magnetic bead can be, for example, attached to a pathogen which you want to register or detect, and then you detect it or measure it via the magnetic sensor. Here, what you see is a composite material. This is a Plight Pen, which is a thermo-responsive composite filled with magnetic nanowires. And in a magnetic field, you can actually change the size of this droplet considerably by around 50%. And the droplet is filled with a drug. And in this way, you have a remotely controlled drug delivery device, which allows you to release drug on demand. Of course, the drug droplet can be implanted inside of the body, and you can release multiple times through a magnetic field. And a rather recent development, of course, in the drive to prepare and fabricate flexible sensorics, there is now also flexible magnetoelectronics. And we find a couple of different magnetic concepts realized as flexible magnetic sensors. For instance, the giant magnetoresistance sensor, which we have different realizations by now. For example, in this case, they were fabricated in a standard microfabrication process, these giant magnetoresistance materials. Then they were broken into flakes. The flakes were mixed into a paste, and then the paste was painted onto a substrate. In this instance, the giant magnetoresistance sensor was microfabricated directly onto a flexible substrate. We have anisotropic magnetoresistance sensors fabricated on flexible substrates. The Hall sensor has been realized already. And finally, also the tunnel magnetoresistance sensor, which is the most modern thin film magnetic field sensor, but it's also the most fragile and hardest to fabricate one. And it was only realized in 2017 as a flexible sensor. A peculiar thing about magnetic sensors is that the magnetic fields they have to detect span an extremely large range. The typical fields for biological signals are in the femtotesla region, or between the pico and femtotesla region. And then as you go, this is compared, for example, to 40 microtesla, which is typically the field of Earth. We have magnetic storage media with a millitesla. Permanent magnets can go up to about 1 Tesla. The strongest electromagnet can produce around 5 Tesla. The strongest superconducting magnets we have can maybe produce around 60 Tesla. But in this galaxy, there are even fields that go up to 100 megatesla. But of course, we are not interested in those. We're interested in these types of fields, but even they span the power of 17, for example, which of course is a range that not one single sensor system will be able to measure, but depending on your application, you will use different sensors. And for the lowest field applications, we use superconducting quantum interference devices. Then we have the very well-known flux gate sensors. They are actually quite sensitive, but they are made with coils and cores. They are heavy, they are bulky, they are power hungry. And then we have the dominant sensors, Hall effect, and magnetoresistive sensors, and also magnetoimpedance sensors, which are less well known, but I'm gonna give you a little overview of them today. Now, the market of magnetic sensors is dominated by the Hall effect sensors, followed by magnetoresistive sensors, different types of magnetoresistive sensors, but mainly the anisotropic magnetoresistance sensor. And also in the coming years, this will not change too much. The magnetoresistance sensors will slightly take some market shares from the Hall effect sensors. The revenue is in the billions of dollar range and keeps growing considerably. And if we look at publications about magnetic sensors, then what we find is this green area covers biomedical applications, which is almost 50%. So it's the detection of ultra low magnetic fields, followed by a couple of other applications like non-destructive testing, of course, navigational purposes, and flexible electronics also has taken over quite a share. All right, then I'd like to go into the first sensor element, the Hall effect sensor, and I will briefly introduce you to the method or physics of these sensors before I go into some applications. Now, the Hall effect sensor is quite an old device. It has been discovered by Edwin Hall, and that was already in 1879. And then it quickly was used in many applications. And for instance, this is, I think, iPhone 3, I'm not sure, but it has used a Hall effect sensor bridge like this for the detection of the Earth's magnetic field. And Hall effect sensors are typically used in the bridge, and the main challenge is to balance the offset of the sensors. Now, the Hall effect relies on the so-called Lorentz force. And for those of you who are not familiar with that or have forgotten about it, it is a force on a moving charge if the charge is exposed to a magnetic field. And let's say if we have electrons, and the electrons move through this conductor, and we have a magnetic field perpendicular to its movement, then we will get a Lorentz force that drives the electrons to the direction that is perpendicular to both the current direction and the magnetic field direction. When this happens, of course, then we get a deprivation of charges on the other end, and this causes the buildup of an electric field, and we can find the equation for force equilibrium, and from that we get the so-called Hall voltage, which is the voltage upon the application of a magnetic field. And this voltage has a few really nice features. One, it is proportional to the current that you send through. So the higher the current, the higher the signal. It is proportional to the magnetic field. This is, of course, a very attractive feature for a sensor when you have a linear response. It's inversely proportional to the thickness. This is particularly attractive for fabrication because this sensor is actually very simple. All you need are 4 electrodes, 2 to send the current through, and then 2 other ones on the sides to measure the voltage. On a thin conducting structure means that you can, for example, use a very basic MOSFET structure and just have to add 2 electrodes. So it is compatible with standard microfabrication and silicon processes and can be implemented easily on any die. Also, it is inversely proportional to the mobility of the carriers, and this means that semiconductors are much more suitable than conductors. And for instance, in silicon, you have a Hall effect of about 10,000 times more than in copper or gold. And because the charge type will change the sign of your voltage, you also can get a measure for the type of charge you have, whether it's a positive or negative semiconductor. And on top of that, the charge carrier density will also affect your voltage indirectly. So it gives you also a method in semiconductor fabrication to measure the carrier density of your charges. Now, I'd like to show you one type of Hall effect sensor that I have been working on, which is based on a very recent fabrication method. And this is called laser-induced graphene or laser Scribe graphene. And it was discovered 6 years ago. And it's a very simple method. All you need is a laser. Typically, you use a CO2 infrared laser, and then you scribe graphene on a substrate, which most of the time is polyimide, like Captain. And it works basically like a printing process. But what you end up with is porous graphene on top of the polyimide. And you can make, of course, arrays of this substrate, of these sensors. You can make any kinds of shapes. You have a lot of degrees of freedom, like in other printing techniques, and you have a flexible version of this. We realized different types of Hall effect sensors with different structures. And in this cross-section view, you can see the graphene flakes on top. It's a very porous structure. This is about 30 micrometers thick here. And because it's so porous, it's very attractive for chemical sensors, of course, because of the large surface area. At the bottom, you see the remaining PI. In this case, this is about 120 micrometer. And it has a few very attractive properties. For example, in this thermal gravimetric plot, you can see that the structure survives temperatures up to maybe 500 degrees. This here shows you the Raman spectra, which the peaks indicate the graphene. In a single layer graphene, for example, this 2D peak would be more pronounced. So we have here this porous graphene flake structure. Now, in case of the magnetic field sensor, the Hall effect sensor, the basic setup is very simple, and we measured the response, and as expected, it has a linear dependence on the magnetic field. We measured fields up to actually 6 Tesla. With this, then, we realized a tactile sensor, and we used the flexible LIG or LSG sensor and covered it with EcoFlex, which is a very soft silicon-based rubber. And on top of that, we put the magnetic skin. I'm gonna show you more about magnetic skins later, but it's basically a flexible permanent magnet. And then when you squeeze this structure, you will change the separation distance between the magnetic skin and the Hall effect sensor, and this gives you a pressure, force, or tactile response. As you can see here, and also this response is a linear response, and can be realized now on different geometries to satisfy different use cases. We tested and characterized the sensor considerably. When you bend it, for instance, static bending, it is more or less a constant signal, but actually when you bend, when the radius becomes smaller, your sensitivity or your output voltage will drop slightly. And this is a geometric feature, because the Hall effect depends on the magnetic field perpendicular to your structure. As you curve it, there will be less apparent field, and that's why you also get less signal, even though you have the same amount of magnetic field. But when you release, you actually come back to the original signal. We tested the dynamic response for 1,000 bending cycles. We tested it for 3 different sensors, and as you can see, it's a pretty stable signal that does not deteriorate. As I mentioned, temperature, the temperature durability is an attractive feature, so we also put it in a temperature test system, and we measured the Hall effect up to 400 degrees Celsius without any noticeable degradation or change in the signal, which leaves this sensor with, or gives you the opportunity to use the sensor in harsh environments. Consider also that this sensor is corrosion resistant. In combination now with the temperature resistance, you have actually a quite capable magnetic field measurement device. In terms of noise, we characterize the noise, and we have 1/f noise that has a corner frequency of at around 20 Hertz, and then we find the thermal noise floor at 54 picovolts per square root of Hertz. This is a very low value, so it's actually quite good, but it depends, of course, mainly on the resistance of the device, and since it's rather big, it can be expected. Now, these sensors, as I said, this laser-induced graphene is a quite capable method, and we realized also other sensors, and I'm slightly deviating from the topic, but for instance, you can easily realize a salinity sensor or a flow sensor, pressure sensors, temperature sensors. We use them on animals like dolphins in combination with tags to measure their speed. We use them for pulse rate, heart rate monitoring. It shows you the capability of this fabrication method, and you can integrate all this in a flexible wearable system, whatever now the shape would be, and you can obtain a very competent multifunctional variable sensor platform based on this laser-induced graphene, which is a very durable material. All right, I will move on to magnetic-resistive sensors. And magnetic-resistive sensors have a different working principle. In this case, what you get is a resistance that is dependent on the applied magnetic field. So it is, if you like, it's the magnetic equivalent to the piezoresistive effect. And typically, a magnetic-resistive sensor or material is characterized by the magnetic-resistive ratio, or MR ratio, which is simply the maximum change in resistance that you get upon applying a magnetic field over the original resistance without the magnetic field. And the most common types of magnetic resistance are the anisotropic magnetic resistance, or AMR, giant magnetic resistance, GMR, and tunneling magnetic resistance, TMR. And I will focus mainly in this presentation on GMR and TMR, and just briefly introduce you to AMR, which is an effect that is long since known, was discovered by Lord Kelvin in 1857 already. And it actually is an effect that occurs in every material where you send a current through. As you apply a magnetic field, the current will depend on the direction between the current and the magnetic field. And this is caused by the direction dependent scattering of electrons, and you get the highest resistance if your magnetic field is parallel to the current, and you get the lowest if it's perpendicular to the current. So it's very easy to implement, and this is why these sensors are prominent and are still the most versatile and commercially most used magnetoresistive sensors. The effect shows a very non-linear response. That means, for example, at zero field, you have actually zero sensitivity. That in turn means you have to somehow get your operating point, for example, to the middle, which is typically done either by a specific electrode configuration or by biasing magnetic fields, which are fabricated through a permanent magnet or other solutions together with actual sensing element. In any case, it is very easy to fabricate and therefore it's very popular. But I want to rather focus on newer technologies. But just one thing to remember here, the anisotropic magnetoresistance ratio typically is in the % range. So it's a small effect. And this is the advantage of giant magnetoresistance sensors, for instance. Now, the giant magnetoresistance sensors are interesting for many reasons, but one thing that is outstanding, these were the first spintronic devices actually. And in spintronics, we use the charge of an electron, but also its spin. And the spin can be used to realize non-volatile systems or memory effects. And it can be implemented in many different ways, but one feature, for example, is that spins can move between electrons without the electrons actually moving, which means you can have a spin current, or you can move information without the heat losses that you have when charges are moving. So it can be used for implementing very low power consumption devices. And while this has been a field of research for a long time, it actually, besides the GMR sensor, we see now more and more devices coming out, especially in the memory area. Now, how do we actually use the spins? Well, first of all, in a magnetic material, we depend on the spins anyways. Let's say you have a magnetic material that is not magnetized. Take iron. The magnetization of iron mainly stems from the 3D shell. And if it's not magnetized, then the up and the down spins of your electrons will be equally present up to the Fermi level. But if you have your material magnetized, then there will be a splitting of the two bands, of the two energy bands for the up and the down spins. And at the Fermi level, you will have more up spins, which we call the maturity spins, and they determine the magnetization direction, than down spins. But there's one other particular feature. At the Fermi level, the width here determines basically the density of states. And this density of states at the Fermi level is responsible for the resistance. If you have a high density of states, then there are more scattering sites and the resistance is higher, which means in such a configuration, in a magnetized material, the spins in this, the minority spins, they have a higher resistance, or they experience a higher resistance than the majority spins. And this is utilized in the giant magnetoresistance effect. Just as another information, how can we create spin currents? There are different possibilities, but one very easy one is the so-called pinhole effect. And it happens basically every time you send a current through a conductor, spins or electrons of opposite spin directions will accumulate on different sides of your system. You can think about this in a way. A tennis ball or soccer ball actually moves when you shoot it, and it has a spin. It will curve to one side, and with different spin directions, it will curve to the different sides. In any case, so we are going to use now the conductivity dependence of the different spins in magnetic materials in this GMR sensor. And it actually is a pretty simple configuration, at least schematically. You have only 3 layers. A magnetic layer with a fixed magnetization direction, so it's a hard magnetic layer, and non-magnetic conductor, and then you have another magnetic layer, which is soft magnetic, so its magnetization direction will change with the magnetic field that you want to apply. And we just look now at 2 easy, simple cases where we have a parallel magnetization condition and an anti-parallel magnetization condition. Now, as we know from before, the resistance, the two different spin states experience is different. And the majority spins will have a low resistance, then you go through a conductor and another low resistance, whereas in this case, the minority spins, they will have a high resistance, conductor, high resistance. We have therefore to look at this, not with the basic Ohm's law, but we have to look at the current densities for each of the spin directions, and then we add up these two. And this is done through MODS2 current model, where for the two spins, we have two paths. And in this case, we have a path with low resistances and a path with high resistances, which overall, of course, is a parallel. If we have, if we do have an anti-parallel configuration, then we will have low resistance, but here we face a high resistance. And here we have high resistance and low resistance, which means each of the parallel paths has a high resistance. In turn, this means we have a high overall resistance. And this is the concept of the GMR sensor. And if this direction here of the soft magnetic layer is somewhere in between, then we get a resistance somewhere in between. And the discovery of this effect, of course, was extremely important, and it was worth the Nobel Prize in 2007 for physics for Albert Fert and Peter Grünberg, who discovered it, and they discovered it actually independently in different institutions. All right, so the effect is again very non-linear, and we have a similar issue as with the anisotropic magnetic resistance. At zero field, we have in this configuration here zero sensitivity, but this is relatively easy to get hold of. What people typically do when they fabricate these devices, they induce a magnetization of the soft layer that is transverse to the one of the hard layer, and that puts our operating point right in the middle of the sensitive region. And then we basically move to the left and to the right like this as the field goes up or down. And with the Chimera resistance sensors, we can obtain tens of percent, 30, 40%, almost 100% of resistance change. Obviously, that's a much stronger effect than AMR, and therefore sensors can be much more sensitive. And this was back then in the mid-90s, roughly. This was a big push in the density of hard drives when we were able to actually measure much smaller fields. Now, I'm going to show you a concept of a biosensor, which I realized with these Chimera resistance sensors. And it's the so-called Bead trap detector. And the concept of using magnetic particles for biosensing is quite popular because these particles can be easily fabricated, and they're biocompatible iron oxide particles. And when they are functionalized with a coating, they can actually attach to specific pathogens. This can be a virus, or this can be a bacteria. It can also be a DNA if you want to use it for extraction of DNA. And in the case of the Bead trap detector, the system is pretty much straightforward. You have a trap, a well, and if you turn on a current in a conducting line underneath, the magnetic field from the current will attract the beads into the well, and then you have a magnetic sensor which measures the signal from these beads. Now, let's assume that the beads actually have attached to bacteria or viruses, then the size of each bead will be larger, and if you do the same thing, then fewer beads will fill the trap, and you will actually measure a smaller signal if you have captured your target. So the concept is pretty much simple, and it gets even easier when you realize that you don't need this mechanical trap, because the magnetic field sensor will anyways detect only beads from a certain area. So if you have some here and on top, it doesn't detect it. So you don't even need the trap. So it's a planar sensor that is very easy to make with a magnetic field sensor and the trapping conductor, and that gives you the opportunity to detect bioparticles. Now, coming back to the size change, if we take a very common magnetic bead, like a dyna bead, it's about 3 micrometer in diameter. A typical E. coli bacteria is roughly of the same size. So actually the size of the bead changes considerably. The link, in this case with antibodies, is negligible in size with a few tens of nanometers. And you see here such a structure that is used for trapping you can trap beads from a large area through current lines, which you sequentially turn on so that the beads are moved toward the center. In the center, we have a sensor, and then we have here the beads trapped by the sensor, and you measure the signal. And with this, you can detect, for instance, nucleic acid or E. coli. And what you see here, the more the concentration of E. coli, basically the more you attach or capture, the smaller your signal becomes, because fewer beads will fit into your trap. Okay, and this takes me to the tunnel magnet-resistant sensors, which is the latest incarnation of magnet-resistant sensors. And the concept is very similar to the child magneto-resistive sensor. It has 3 layers conceptually. Again, with a hard magnetic one, a soft magnetic one, but it's separated by an insulator instead of a conductor. So the electrons have to tunnel from one to the other end. And it was discovered in the mid-90s. And now we can get magnetic resistance ratios of even up to 1000%. So it's an extraordinarily sensitive detector. And the TMR ratio is defined in the very same way as the GMR ratio or the MR ratio in general. And we again have to consider the different spin directions indicated with arrows and parallel or anti-parallel configuration of the magnetization directions. So here is this shown schematically. We have 2 magnetic layers, or sometimes called electrodes, separated by an insulator. And the electrons need to tunnel from one to the other magnetic layer. And this tunneling has a certain resistance that's associated to it. And this resistance depends on the density of states at the Fermi level of the specific spin direction in one layer and the other layer. In particular, it depends on the product of the density of states. So let's take, for example, here the parallel configuration. Then the majority spins have a low number of density of states multiplied by a low number on the other side will be high resistance. We are basically here. Whereas the minority, they have here a high number and they have a high number here. So this will be a low resistance. We end up with a configuration like this in the MODS2 current model. If we have an anti-parallel alignment, then we have a low density of states and a high one, the product will be small, and the high one multiplied by a low one, the product, it will also be small. So we have the situation like this, where both paths have a high resistance, and therefore the overall resistance is high. In reality, of course, the tunnel magnetic resistance sensors are not that easy to build. The tunneling structure is very, very delicate and consists of a large number of layers to accommodate different crystal structures and the different strains that are created during the buildup, and also to accommodate a thin tunnel barrier. In this case, it's MgO. That's a tunnel barrier. It's slightly more than 2 nanometer in the schematic, but they can be also less than 1 nanometer. And this means, of course, there are not many instruments which can fabricate such a tunnel magnetic resistance sensor. And but industry got control over the parameters, the process parameters, well enough to do this now on a routine basis on large wafers. And it is used not just for sensors, but it's also used for memory elements. And why is that? Because you can tune with the dimensions of the layers, you can tune the characteristic curve to look either like this with the big hysteresis, can be even much bigger than that, or with a small hysteresis. Obviously, this is a very good sensor, and this can be used as a memory with 2 states, a high and a low state. Now, I want to show you how to make flexible tunnel magnetic resistance sensors, which can then be used as wearable devices on, for instance, also very small structures. To make a tunnel magnetic resistance sensor flexible, you have to resort to a method that utilizes silicon. Because of this extremely thin layers, you cannot fabricate TMR sensors on polymers because the surface roughness will be too high. At least so far, no one accomplished that. So what you do is you fabricate it on silicon, as you would usually do when you make a TMR sensor. then you protect them. For instance, with photoresist, you turn it around and then you etch or reduce the silicon layer thickness on the backside to the desired thickness. In my case, I typically go down to about 10 micrometers. And then you have a flexible silicon with the tunnel magnetic resistance sensors on top. And if we look here at the characteristics of that, you see here flakes of this or pieces of these tunnel magnetic resistance sensors that are flexible. And the magnetic properties shown here, saturation, magnetization, coercivity, and remanence, as a function of the bending diameter, do not really change. We have here high resolution transmission electron microscope images that show that there is also no degradation in the layers. We see here this thin red line is the tunnel barrier. Here are the resistance values and TMR ratio, and they also do not change with the diameter of the bending radius, and we also tested this again over 1,000 cycles and haven't seen a degradation. The noise also does not show dependence on whether it is regular 500 micrometer thick silicon or 10 micrometer thin silicon. And I use this for a very specific application where it was worn on a cardiac catheter. And the demand for this came from the fact that in cardiac catheterization, you insert the catheter to go along the artery into your heart. And this is a minimal invasive method that is used for angiography or to repair heart valves and also to insert stents, for example. But in order to visualize the catheter, you have to take an X-ray video while you are under this procedure. And in order to see the vessel, you have to inject the dye that is intransparent to X-ray. And this is how the method works. And what the cardiologist actually was in need of is he wanted to reduce X-ray and dye because they have quite some side effects. And in order to do so, we wanted to implement orientation sensor at the tip of the catheter, which would indicate the cardiologist the orientation of where the tip is pointing. And with this information, he can use much less of the X-ray and dye. He can basically turn it off while he does a lot of the insertion of this catheter. Now, this is challenging because these catheters are tiny. The sensor must not increase the thickness or weight too much. And the power consumption must also be low because you have limited availability there with the wires. So we utilized these flexible tunnel magnetic resistance sensors because there was also a need for high sensitivity so that you can detect the earth magnetic field and a direction change being indicated through the earth magnetic field. And here you see one of these examples. There's the catheter. Here is the tip of the catheter. If you zoom in, then you see here tunnel magnetic resistance sensors glued to the tip with a super glue. This is a different method where we put the tunnel magnetic resistive sensor die. You see the flexible silicon here, the gray structure, on a double-sided adhesive tape, and then we basically mount it by means of this adhesive tape. And there is the result of such a sensor, which has actually a high sensitivity of 9 ohms per degree. It only weighs not even 10 microgram. The thickness is increased just by about 10 micrometer, and the power consumption was 30 nanowatts. All right, and this takes me to the giant magnetic impedance sensors, which are probably a bit less known, even though they are extremely sensitive and one of the best commercial sensors that I'm aware of is actually a giant magnetic impedance sensor. And this effect is also pretty simple, and this is probably why it is a very attractive device of sensor type. And it was originally realized in microwires, soft magnetic microwires, typically coated with glass. And the effect looks like this. It has a very high sensitivity with impedance changes of hundreds of %. And basically what you do is you send an AC current through even just a ferromagnetic material, and this AC current will magnetize the material, and an external field will change this magnetization. And this in turn affects the inductance of your structure, and thereby you get an impedance change. And if you make the structure a little bit more complex, but still only, for example, 3 layers, then you get a very nice response. And the thin films, of course, are better to integrate. And this is what I focused on, fabricating chimera-impedance thin films. And structurally, these 3 layers are permalloy, which is iron nickel. It's very easy to make, copper and permalloy. And the thicknesses are also easy to realize because they are in the hundreds of nanometers. And this means you have a very simple structure that is also very robust. Then another interesting feature, the sensitivity is high. We get per sense per Ørsted. So we have a sensor that can easily detect changes in the Earth's magnetic field, for instance. And the sensitivity depends on the frequency, and we can measure at very high frequencies that are compatible with ISM bands, and we have a really high sensitivity that allows us to use a wireless operation. All right, so how did we implement this? First, we used it with so-called surface acoustic wave transponder, which is a common device. It's also used in RF circuits because of filtering, for example. But in a transponder, what you have is an interdigitated electrode that initiates surface acoustic wave through the piezoelectric effect. It's connected to an antenna, and the radio signal, it checks this surface acoustic wave. We have here a so-called delay line. The wave travels across the substrate. Here is another interdigitated electrode from which the wave gets reflected and goes back out. And you can load this interdigitated electrode with the magnetic field sensor, the GMI sensor, and this will change the reflection. Here is a sensor fabricated compared to a coin. This is a zoom in of the interdigitated electrode. And here is a time domain response of such a sensor, where here we have the reflection of interest. We have other reflections that come, for example, from the ends of the structure. And with this sensor, we achieved a resolution of 3.5 milliOersted, and that, for instance, is sufficient to detect a car that drives on the road when you embed your sensor into the road, because the car signal is about 0.2 Ørsted compared to the 3.5 milliOersted that we can measure. So you can, for instance, think of this sensor being implemented in the road. It doesn't need wires, it doesn't need a battery. It's a fully passive system that responds to cars and that can be used for tracking cars, monitoring empty parking lots, etc. You can add additional functionalities, humidity sensing, temperature sensing to the magnetic field sensor, and then you end up with several signals, each one of them containing a specific information. You can run all 4 of them in parallel, and you still can extract them after you calibrated the signals. And this can be used now, for instance, for power grid monitoring, where you can, through the magnetic field, monitor current. You have the humidity and also the temperature control directly included in this, but it's wireless and can transmit the signal somewhere down to the station here. For instance, it can be used for structural monitoring, where cracks and gaps and corrosion changes the magnetic signature. It can be embedded in the building when it is fabricated, because it doesn't need power. It can be read every year and will, after 20 years or 30 years, give you an information of whether the signal changes or not. And of course, it can be used for corrosion monitoring. Now, I used this as one of the first sensors that I actually made flexible back then because of the simple structure. And I fabricated the GMI sensors on different substrates to see if there's an influence of the substrate itself. And these are the magnetization curves of the structure on top of different substrates. And obviously already there, you can see there's a big difference. And what we notice is that the coercive field or hysteresis becomes wider for different substrates, and this width corresponds to the surface roughness. The rougher the surface, the wider the magnetization loop. This is a well-known effect because surface roughness is basically pinning sites for domain walls and will make it harder to change the magnetization direction. And this affects the GMI ratio, where the material with the lowest roughness, Kapton, has the highest GMI ratio, and then of course also the maximum sensitivity it is the highest for Captain. Now, how can you use this? Well, I use this to make an artificial wearable skin. And it was inspired by a biological system, which is the cilium. Cilium is basically a microscopic hair, which is used by many animals, also humans have it for different purposes, either as chemical receptor or as mechanical receptor. And as a mechanical receptor, when you bend the cilium, the neuron will shoot a signal. And we modeled this, we emulated this actually with a micropillar made of a polymer filled with magnetic material that creates a permanent magnetic field sensed by the giant magnetoimpedance sensor underneath. And if a force bends the micro hair, then the magnetic field will be changed. You see here one of these cilia or hair arrays. Obviously, they are easy to fabricate in different dimensions because this is a master mold process which we used. By changing the dimensions, you can tailor the sensitivity. And I started with giant magnetoimpedance sensors, but eventually I used also giant magnetoresistance and tunnel magnetoresistance sensors for this application. And because it is a magnetic system where the sensor is underneath, embedded in the silicon or Captain, it can operate in air and water in the same way without a change in the signal. And here you see now the artificial skin on a glove, for example. You see here the different pillars. It can be used to monitor the heart rate. It can be used to read Braille, which are the letters, the letter codes blind people use. It can be used for fluid sensing because the fluid flow will bend the cilia, and actually we achieved an extremely high resolution of 13 micrometer per second in water. The power consumption was only 80 nanowatts. And here you see how you can tailor the response with a higher sensitivity or a larger range simply by changing the diameter of these pillars. And that takes me to magnetic skins, which we use in combination with flexible magnetic field sensors to make flexible magnetic sensor systems. And you see here a couple of examples. The black structure is always the magnetic skin, which is basically a very soft, stretchable, flexible, permanent magnet. And it's easy to fabricate. You use a polymer matrix, mix it with magnetic powder, magnetic nanowires, depending on what you have available, and you can fabricate all kinds and shapes of magnetic skins. You can also paint them in any kind of color so that it can be worn on your skin and either look chic or it can be camouflaged and have the color of your skin. You can easily tailor the properties. If you add more filler, you can make it stiffer. Also, if you add more filler, you can increase the remanence magnetization. So you have options to customize it to your use case. And one of the use cases was animal monitoring, where you see here our system that we developed, an embedded system with tunnel magnetoresistance sensors combined with the magnetic skin on a turtle in this case. And there was an app that would record the movement of the turtle. We also used this on giant clams. We used it on crabs, and there was always, we did this in collaboration with marine biologists, and they used the biocompatible glue. And with this, then you can, for instance, monitor the giant clams opening and closing as a function of day and night, or as a function of predator proximity, turtle movement, and so on in their natural behavior, with very little impact on the animal. On top of that, we used it to track eye movements, and we basically put magnetic skin with Vaseline on the eyelid. And first we were wondering whether, well, we actually came up with this idea because the magnetic skin is extraordinarily soft, well, at least the version that is made with EcoFlex. And we measured the softness. And for instance, this here is the tensile stress over the strain of the magnetic skin versus the one of a contact lens, AccuFlu. And as you can see, the contact lens is actually stiffer than the magnetic skin. So while you have to get used to it at first, like with a contact lens, you immediately forget that you're wearing it. And with the magnetic skin on the eye and the sensor in eyeglasses, you can detect whether the eye is open or closed, but you can also detect whether you look left or right or up and down, because the magnetic field that is straight from this magnetic skin detected at the sensor depends on the direction of the sensor. We use the 3-axis sensor, and in this case, for example, the field parallel to the sensor is not affected by looking left and right, whereas the one that is perpendicular to the sensor is affected. The reason is, by the way, that the eyeball is not spherical, but has slightly different curvature, and therefore, as you move up and down, the magnetic skin moves further out or in. So you can actually use this to monitor the eye movement, which is interesting in sleeping labs or for certain eye diseases. But we extended this actually to monitor the eye and also other facial gestures. And with this, together with the eyeglasses, we developed an electric wheelchair that is completely controlled by facial gestures, where the user only wears the glasses and the magnetic skin in a certain location on the eye, for example. And then with facial gestures, the user can control the wheelchair. And this brings me actually to the end. And I would like to thank you very much. And of course, now, if there are any questions, I'm more than happy to take them.
Yeah, thank you. Thank you very much, Jürgen. It's open for the comments and questions. Actually, I would like to start. So the last one, the magnetic wearable magnetic sensor, two things. One is that how do you supply power? And second thing is that what is the effect of external magnetic field?
Right. So the magnetic skin itself does not need power. It's a flexible permanent magnet. The magnetic sensor that we embedded in the eyeglasses needs power, and in this case we used a button battery. And so the second question was? Is
the magnetic skin. So okay, so if it does not need any power, so then the question will be that when you read any kind of stretch or movement, then the reader will have some kind of RFID kind of system, is it?
Yes, that could be if in this case, for example, with the wheelchair, we had that to communicate from the eyeglasses to the wheelchair. We use Bluetooth low energy.
Oh, okay. Yeah. Yes. So the second question is that what will be because so if you use it for quite some time, and external magnetic field as well as Earth's magnetic field might actually influence it. So the characteristics might change with time. So how do you ensure that the performance will not be very much degraded with time?
So actually, now coming back to the question with the Earth magnetic field influence or any external magnetic field, we take care of this by using a reference sensor. So in the eyeglasses, we have another sensor that detects the same environmental field as the sensor for the magnetic skin, but it is in a different location. So we have one sensor that detects the environment magnetic field plus the one of the magnetic skin, and we have another one that only detects the environment, is too far away from the magnetic skin, and if we subtract the two signals, we get a very nice differential measurement actually to get rid of these external disturbances.
Okay. I mean, basically, you are always like a calibrating kind of things with okay. Yeah. So anyone has got any questions or comments for Jürgen?
I have a question.
Yes, please.
Hello?
Go ahead.
Hi, that's a fantastic talk. Thank you so much. Do you have any experience recording sounds from the body using these wearable sensors? And have you considered gut sounds? We have an interest from the neonatologists, the preterm babies, who want to measure sounds from the gut.
So we actually have not used our sensors to measure sounds. We never did that. I know that, for instance, laser Scribe graphene has been utilized as a sound sensor attached to the skin on the throat. I did not myself do that. However, I used the magnetic skin actually in a neonatal application, preterm especially, where we equip a catheter, a umbilical catheter with magnetic skin, and then from the outside with the magnetic sensor, we can detect the position of the magnetic skin, and therefore we can locate the tip of the umbilical catheter without the need of any X-ray.
Very important.
Different application, but
yes,
but it turned out that this is very useful because neonates, because they're so tiny, the magnetic field range is sufficient to detect the catheter from the surface of the skin.
That's good.
Wow.
So I didn't show this application, but this would be another one, yeah.
Okay. Yeah. Anyone has got any other comments or questions for Jürgen?
Sure, I have a question. Am I audible?
Yes, yes, we can hear you.
Yeah, thank you, sir, for a wonderful talk. I just wanted to know that if from a magnetic skin, like you showed, can we measure all parameters related to the blood flow?
You want to measure parameters of the blood flow?
Yeah, like oxygen saturation and all that. Can we measure? Can we measure the parameters of blood flow using a magnetic skin? Is that possible?
So, yeah, there will be some parameters you can measure. Obviously, the heart rate we did measure. And
yeah.
I can imagine a chance to measure blood pressure because of the increased deformation that you possibly get on the skin surface or wherever you take it. Oxygen, I don't see how that would work.
Like a hemoglobin content and all. Do you have any? Okay. So again, so from what I understood, this magnetic skin will be there, and you need another sensor to detect, right? The magnetic skin doesn't do any sensing, but a sensor is detecting it. So for whatever parameters you, for whatever application you may use it, you need two sensors to detect the ambient field as well, right?
Yeah, most likely, yeah.
Okay, so I just wanted to know about that. Like, what if some other metal or something also comes in between, like, which would alter the magnetic field? Normally, normally I have seen some casings like that for any magnetic devices to avoid external field. So for these biomedical applications and all, I don't think a casing is a convenient option. So this differential measurement is always done. Is it like that?
We always do the differential measurement. It is something very easy to implement, and because magnetic field sensors are literally super cheap, being the ones we use about $1 each, and we don't buy large numbers. It's always easy to do that. Maybe there is a use case where you cannot have a reference sensor far enough away. Maybe this would be a problem, but since we did not come across this problem yet, we always had a solution. Yeah.
Okay, thank you, sir. Yeah.
But for example, if you really would put a soft magnetic material between the sensor and the magnetic skin, then you could not see the magnetic skin anymore because the soft magnetic material would shield the field of the magnetic skin. However, this is unlikely.
Yeah. Okay, sir, I understand. Yeah. Thank you.
Thank you, Sandra. Anybody has got any other questions? I have got one more, Jürgen. So you talked about the wearable sensor, but what is the future for using a magnetic sensor as implanted sensor? Do you think any future there?
So there's a future for magnetic sensing in biomedicine. For instance, there is a company that since a couple of years offers a robotic surgery system where you have magnets, permanent magnets, on the devices, and with external magnetic fields, you control the movement of the devices inside of the humans.
Okay.
And of course, there, the sensors and so on are important for the location. Sensors inside of the body, I'm not sure. I'm not sure if there is a need. Sensors on instruments, yes, because with the magnetic field sensor, you can realize a lot of things. Not just, of course, there's the orientation, there's the position, but you can also realize tactile systems and so on. We'll see probably more and more of these smart medical instruments as we go further into the future with robotic surgery and remote surgery. But this did not pick up as quickly as it maybe was anticipated 15, 20 years ago already, simply because of the costs.
Yeah.
Right? I mean,
yeah.
There are not many hospitals which can afford the cost for such a system.
Yeah.
Or insurances, which insurance would pay for that?
Yeah, no, that's good. Yeah, thank you. Is that anybody has got any other questions before we finish the session? So it doesn't look like. So I'd like to thank Jürgen to take your time, and it's early morning in Austria, and sharing your research activities for last so many years. It was really, really interesting, and it was really for many of us who do not work on this area to know lots of activities going on in this area. So thank you very much. And on behalf of the IEEE New South Wales Sensor Council chapter, we'd like to express your heartiest thanks for sharing your research and your time. Thank you very much. Have a nice day.
You too. Goodbye. Thank you very much.